All right, this is part three of our lecture two. Finally, we're getting into the sensing devices and what is um, image acquisition and image sensing. We're getting into the actual engineering part of the topic. But basically, what it is that you have some sort of incoming energy. That could be a radar signal, an X-ray, infrared, sound, or light, right? We're talking about vision. I'm talking about in a broader sense of image processing here. So this signal is transformed into a voltage. Transformed into a voltage by a combination of input electrical power and sensor material that's responsive to the detected energy, of course. Of course, you cannot use a sensing device that senses X-rays to the same thing that senses infrared or any other sort of energy. The output is a voltage waveform. That's basically what's the response of the sensor. And the digital quantity, what we want to analyze is a digital image. So from this waveform, this analogic information is transformed into digital quantity by a process that's called digitalizing this response. Before we get into the nuts and bolts of digitalizing, that's basically what we're talking about. So there's some energy coming, depending on what sensing device you have. You have some sort of filter, and this is the sensing material that's sensitive to the incoming energy, and the output is a voltage waveform. So imagine that a sensing device, this is a single sensing device that's capturing a small portion of this energy. You can have this sensing devices, an array of these units of sensing devices, a linear array where you're picking up, you're describing your energy in a linear form, or you can have a matrix, right? Where if you want to imagine that you have a, let me get a pen here. So you have, I don't know, some object, a mountain here, and this sensor device is going to pick up the energy from lights emitting in this mountainside, and is going to be reflected and perceived, or acquired, I should have said, by this sensing device. Is that clear? So that's our sensing device. This is an actual image, microscopic image of our fovea, of a human fovea. So you see these small bits here. Hey, these are the cells, right? The cells, the rods and cones. I'm sorry, I can't distinguish which one is rod and which one is cone. I'm not a neuroscientist or a biologist, but you can see that there are distinct kinds of cells here. And this is, well, I can't say that exactly the same, but that's this, right? This is what we're talking about. So in a certain sense, each one of these little cells in the human fovea is one of these sensing devices that we're talking about in this slide. Okay, right. So, and even in the human visual system, the energy that's picked out by these sensing devices is transformed into a voltage, into electric. This is an actual signal observed in when you observe in a cell like this, in a tangential section like this. So you see that increase in firing rate is driven by external stimulus. So here it picked up something interesting, and this was excited in some, not as much. This is not excited at all. So they picked out something. This is the signal that the human visual system emitted when observing something, right? Okay, so in a digital image, that's similar, right? So we have a scene here, an imaging system that's basically this, right? Some sort of imaging device. And this is the internal image plane. And the image that's picked out from the real world is now transformed into digital signal, into a digital representation, and by two processes that we're going to see in the next slide. So just bear with me a second. So what we see is this. This is a digitalization of the image as picked out by the imaging system. And the processes that are used in this digitalization process are called sampling and quantization. So imagine this is the same scene that's been observed by this imaging system. Imagine a cross section here, cutting from this point A to point B. So the imaging system in this cross section is going to get a signal, an analogic signal, that's basically the intensity, the whole variation of intensities here, intensity in this case, intensities of the energy, and it should transform to a digital form. And it does that by sampling. It would be crazy, right, to represent the whole bunch of information here. You can do it, and some people do it, but normally what we do is a sampling, where we, as the name says, we sample pieces of this information, and these pieces are now used. This is what we see in the. This is what is stored as an image when you're taking a picture with a mobile phone or with a digital camera. And this sampling is actually digitalization on space. But we also have another process that's quantization. Quantization is going to pick up every single intensity of energy and transform to in intensity in pixel. And obviously, if you're dealing with the digital world where everything is stored into bits and bytes, I cannot have a continuous signal of intensities, right? A continuous dense representation of the intensities. What I'm going to have is a quantization, a discretization in terms of intensities of every signal, of every sampled point. So what we have from a signal that's full of information here, and full of noise as well. When we move to the digital space, I have a sample. This signal sampled in space at the same time that is sampled in intensity. That's the process of sampling in quantization, as said here. This is what is stored as a digital representation, as a digital image of whatever you see, with whichever sensor device that you have. Right. So in fact, what we have is, given an image, we have this digital information. And the more information I'm going to get is directly related to the finer level of this quantization and sampling process. But meaning that if I have smaller pieces of sampling here, smaller intervals in the sampling, and the smaller intervals in quantization, I'm going to have a higher fidelity of the image. Right? So that's what when you see that how many megapixels is a camera, it means how many. What is this the granularity of this discretization that your camera does in any image? Okay, so once we have this discretized signal, I have to represent it in a mathematical way, and the way we do it. Now, there are three basic ways of representing a digital image. You can understand a digital image, represent and manipulate. Now we're getting into the actual processing of the image, or image processing. I can manipulate this image as a digital function. The image can be represented as a function, three-dimensional function, or even it doesn't need to be in three-dimensional, it can be n-dimensional. As bidimensional a visual intensity array, which is this this representation here, or what we're going to use throughout this course, the vast majority of image processing in computer vision algorithms that we're going to see. We're going to understand, we're going to manipulate the image as a matrix, where each point in the matrix is going to be representing one point in this image, and the value inside, in the values of the matrix are going to be representing the intensity values of the this digitalization process, again, that's composed by sampling and quantization. So you see, if this is a representation of this, we see that here it has zero intensity, zero intensity, zero intensity, but here I have non-zero intensity. That's represented in the matrix as this has no information in this pixel. There's no information in this pixel, no information in this pixel, but there is meaning there's intensity 0, and this pixel has intensity 0.5, representing there is some stuff in this pixel. All right, and this is represented as an intensity pixel that has a direct relation to the intensity of the signal observed in the world, in the whatever scene you are observing, with whichever sensing device you have. So, what is an image? An image is a 2D function where x and y are spatial coordinates. X and y are representing a position in this frame of reference. The physical meaning of this function is determined by the source of the image. I'm talking about intensity of pixel. I'm already thinking about a digital photograph that you take from a camera, but it could represent, I don't know, intensity of radiation or sound. It can have a frequency of sound if you're dealing in the frequency domain. So this, I try to think about this as in a broader sense, right? It could be any sort of physical intensity or physical quality or physical measurement is stored in each pixel. And the values are proportional to the energy radiated by the physical source. This function is non-negative and finite, so it is limited. So we have it suffered a process of quantization, right? So in quantization, you forced it to have a limit amount of intensities and a limit size as well. It can't be infinite because it has to be stored in a computer. Computer is not very good at storing infinite stuff. The limits of these functions are the intensity or grayscale values. They are usually bound goes from 0 to 1. They are normalized to 1, or they can be normalized to any other values. That depends on your algorithm, that depends on your specifications. Or, as we said here, the visual world and an image in the whole visual world, as we've seen, whatever we see is also stored in represented in a similar way as we represent in a matrix. What we see is a matrix, right? The world, I'm sorry to say, we don't see the world. What we see is a matrix. And now I'll close this lecture with this quote from Morpheus.
Unfortunately, no one can be told what the matrix is. You have to see it for yourself.
All right, I'll see you in a bit for the next part of this lecture.